Continuity. A function is said to be continuous at c if its graph passes through the point at x equals c without a hole, a jump, or a vertical or slant asymptote. Here's an example of a function. Basically, if you can take your finger and you can trace over the function without lifting up your finger, it's continuous. Here we can do that. We can trace over this function, never lift up our finger, so it's continuous. Specifically, it's continuous at point C, which is what we're trying to figure out, because at point C, we can trace over it. This next function is continuous some places. Like for example, on this part of the curve, it's continuous. You can trace over it. This part of the curve, it's continuous. But looking at it as a whole, it's not. As I travel from left to right here, as I get to C, I have to come up here to this point, and then I come back down to lift up my finger. That's called point discontinuity, anytime there's a hole in the graph. Doesn't matter if the hole is just here and there's no point to take its place, or if there's a point to take its place, we still say point discontinuity. This next graph is continuous in some places. It's continuous in this part, and it's continuous at this part. If you examine this as a whole, it's not continuous. As we go and we're traveling from left to right, once we get to C, we have to jump up here to continue on our graph. So that is called jump discontinuity, anytime the graph jumps up or down. This next graph has infinite discontinuity, and that happens because there's a vertical asymptote that the graph is approaching. From the left, it's getting closer to that asymptote, and then as it approaches it from the right, it's getting closer to that asymptote. So at the point C, when the x value is C, this graph is discontinuous. And it's discontinuous because of the vertical asymptote, which makes it infinite discontinuity. Please note though, to the right of C, the graph's continuous. To the left of C, it's continuous. But at point C, it's not continuous, because there, the graph has this vertical asymptote. So which functions are continuous? Easy looking at a graph, but what if you're just given a function? Well, if functions f and g are continuous at c, then adding the two functions, subtracting the two functions, multiplying one of the functions times a constant, or multiplying the two functions or dividing the two functions, so long as you are not dividing by 0, and composing the two functions are continuous at c. So to sum up, if two functions are continuous, and combining those two functions in any way, shape, or form will also give you a continuous function as long as the denominator is not 0. Determine whether each function is continuous. Well, this function is composed of actually 4 functions. 1, 2, 3, 4. Let's examine each of those individual functions. So we have g of x minus h of x minus k of x plus j of x. Well, is g of x continuous? Yes, that's a function that looks something like this. It's continuous. Is minus 3x squared continuous? Yes, that's a parabola that opens down. Minus x, that is a line which is continuous, and plus 3 is a constant function. It's a horizontal line. Since each of those individually are continuous, then that makes this combining of those functions, giving us f of x, it makes that continuous. So we can simply say this is a continuous function, this referring to f of x. What about this function? Is it continuous? Well, let's examine the parts of this function. We have the numerator, which is one function. We have the denominator, which we could say is a different function. Let's say that the numerator is g of x. Is g of x continuous? Yes. Y equals 1 is continuous, so it's a horizontal line. How about x plus 1 quantity squared? Let's say that's h of x. Is that continuous? Yes, that's a parabola. But when you put those together, if your denominator can equal 0, then that makes this discontinuous. So let's see if we can make our denominator equal to 0. So if we can find a value for x that makes the denominator equal to 0, then that means this function is discontinuous. If we square root both sides, and then subtract 1 from both sides, we get x is negative 1. which means this graph is discontinuous. Specifically, what type of discontinuity is this? Well, it's either going to be a hole in the graph, a jump in the graph, or a vertical asymptote, or a slant asymptote. That rarely is going to happen in this class. That makes it discontinuous. For this specific problem, we found x equals -1 from setting the denominator equal to 0. Therefore, this has a vertical asymptote. Since it has a vertical asymptote, we would say that it has infinite discontinuity. If we had found that it had a hole, which happens by canceling a term on the top and the bottom and setting it equal to 0 and solve it, we would say point discontinuity. If we had graphed a piecewise function and found that the two pieces come together in a way that it's not continuous, we would likely say it's jump discontinuity.